In 1939, Ott Heinrich Keller asked a question about polynomial maps resisting full solution for over 80 years. Today, we know it as the Jacobian Conjecture. Mathematicians usually tackle open questions by trying to build a direct counterexample or construct a head-on proof. But with the Jacobian Conjecture, those direct assaults typically hit a wall, yielding very little about the underlying structure of the math. A newly released candidate paper, co-authored by AI Systems, suggests a different route. Instead of trying to solve the conjecture directly, it proposes a systematic method of exclusion. The strategy relies on a structural screening program to map out the geography of what are called binary form factorization spaces. The goal of this mapping is to calculate precise geometric defects. By finding exact mathematical roadblocks, researchers can systematically eliminate almost every affine slice of this space as a viable host for the specific polynomial maps the conjecture requires. By shifting from a search for a needle in an infinite haystack to a process of rigorous elimination, this approach narrows an impossibly broad search into a tightly targeted map of dead ends. The screening begins in a specific geometric environment, the marked common root incidence system. We are looking at binary forms of consecutive degrees, specifically degrees m and m+1, where m is greater than or equal to 2. Look at this equation. It defines a family of hypersurfaces, or divisors, that arise when you track where two polynomials share a root. Each divisor in this family is indexed by a specific linear functional, denoted here by the letter L. The foundational question the paper asks is simple but critical. At what boundary this naturally defined geometric object break apart into multiple distinct components? Pinpointing exactly where and why a divisor fractures, its boundary of reducibility, is the necessary first step to mapping the space. Identifying that exact boundary lays bare the underlying projective architecture. Once we have that blueprint, we can begin systematically testing and eliminating the slices. The paper provides a classification that relies on 19th century classical geometry. It proves that the divisor fractures if and only if its parameterizing functional lies on one highly specific classical surface. This diagram illustrates the tangent developable of the rational normal curve. The curve represents the central sweep of evaluation functionals. Notice how it acts as the fundamental spine, with straight tangent lines extending outward to form the wider developable surface. When a functional has a catalecticant rank of 1, it sits directly on this central spine, splitting the divisor into 3 identifiable components. Moving to first jet functionals on the swept tangent lines, the divisor splits into exactly 2 pieces. Finally, genuine 2-point secants and higher rank functionals exist completely off this developable surface. In this empty space, the divisor remains whole and irreducible as a single piece. This geometric fracturing perfectly aligns with the functional's catalecticant rank and jet type. It provides a complete, exact classification of the entire space. Mapping out this classical tangent developable surface gives modern algebraic geometers exactly what they need: the precise structural coordinates required to start computing algebraic defects. With the projective surface classified, the analysis shifts to testing the associated affine slices to see if any are isomorphic to ordinary affine space. To prove a slice is not ordinary affine space, the authors calculate exact motivic obstructions. Think of these obstructions like a mismatched mathematical barcode. If the numbers don't perfectly align with ordinary space, the slice is excluded. Let's visualize the families of affine slices as this massive matrix. We begin the exclusionary process by looking at the slices associated with the rank 1 functionals. Every slice in the rank 1 case is blocked by a precisely computed growth-indeed class defect, exactly L to the power of 2m plus 1 minus L to the power of 2m. That knocks out our first major group of candidates. Next, the focus moves to the rank 2 secants and first jets. These slices are tested by expanding their Hodge-Deligne polynomials. When we look at the diagnostic positions of these polynomials, we find negative coefficients of exactly -2 and -1. These specific negative Hodge coefficients are incompatible with affine space, definitively eliminating this group for Keller maps. The matrix then tests non-adjacent degree pairs. Here, finite cyclic group actions obstruct contractibility, blacking out almost everything remaining. This rigorous screening matrix successfully eliminated nearly every conceivable candidate in the space. The math proves they are structurally incapable of hosting a Jacobian conjecture counterexample. Look at the sheer scale of the exclusion. Out of infinite potential mathematical stages, the grid has gone dark, except for one single anomaly. This surviving anomaly has a specific name. It is the tangent non-osculating linear quadratic slice. Isolating this exact slice relies on a conditional theorem. The surviving slice is tethered to a strict dependency, an upstream cubic classification from a companion release. If that classification holds up, the math dictates all other positive bi-degree slices are eliminated from consideration. This is the payoff of the entire screening program. This exact slice is the unique positive bi-degree affine source that could, in theory, permit a non-zero constant Jacobian determinant. The next step for researchers is now strictly binary and sharply posed. First, mathematicians must discharge that upstream hypothesis. Once verified, the task is clear. Construct the Keller map directly on this exact slice, or definitively prove no such map can exist. If researchers prove a map cannot exist here, it permanently retires this entire family of factorization spaces as a source of Jacobian candidates. By mathematically fracturing incidence divisors, this AI-human collaboration has taken a sprawling 80-year-old open question and collapsed it into a single highly falsifiable target.